Continuous-Time Fourier Transform, Properties and Visual Derivations. This work presents a comprehensive visual and analytical exploration of the properties of the continuous-time Fourier transform through structured animations developed with MANIM community. Each fundamental property, including linearity, time and frequency shifting, scaling, symmetry, differentiation, integration, convolution, and energy conservation via Parseval's relation, is derived step by step and translated into dynamic mathematical scenes. The continuous-time Fourier transform, CTFT, of a signal x of t is defined as follows. Prove the property of linearity of the CTFT. We begin with the definition of the continuous-time Fourier transform, which expresses a signal in the frequency domain as an integral over time. We substitute the linear combination of two signals into the Fourier transform integral, keeping the constants and signals inside the expression. Using the linearity property of integration, we split the integral of a sum into the sum of two separate integrals. We factor out the constants a and b from each integral since they do not depend on time. Each integral now matches the definition of the Fourier transform of the individual signals x1 of t and x2 of t. We conclude that the Fourier transform of a linear combination is equal to the same linear combination of the individual transforms. Prove the property of time shifting of the CTFT. We begin with the definition of the continuous-time Fourier transform, which expresses a signal in the frequency domain as an integral over time. We now replace the signal with a time-shifted version where the signal is delayed by t0. We introduce a new variable tau equal to t minus t0 to simplify the expression and make the integral easier to evaluate. We rewrite the integral in terms of the new variable tau and update the exponential accordingly while keeping the limits unchanged. We separate the exponential term into two factors, one depending on tau and the other depending only on t0. We take the exponential factor outside the integral since it does not depend on tau and identify the remaining integral. We conclude that a time shift in the signal produces a complex exponential factor multiplying the original Fourier transform. Prove the property of frequency shifting of the CTFT. We begin with the definition of the continuous-time Fourier transform, which expresses a signal in the frequency domain as an integral over time. We now multiply the signal by a complex exponential which represents a frequency shift in the time domain. We combine the exponential terms into a single exponential expression to simplify the integrand. We rearrange the exponent to group the frequency terms together, showing a shift in the frequency variable. We recognize that the resulting integral matches the definition of the Fourier transform evaluated at a shifted frequency. We conclude that multiplying the signal by a complex exponential shifts its Fourier transform in frequency. Prove the property of time scaling of the CTFT. We begin with the definition of the continuous-time Fourier transform, which expresses a signal in the frequency domain as an integral over time. We replace the signal with a time-scaled version where time is multiplied by a constant a. We introduce a new variable tau equal to a times t in order to simplify the argument of the signal. We compute the differential, showing that dt becomes 1 over a times d tau. We substitute the new variable and the differential into the integral, rewriting the exponential accordingly. We account for the effective scaling on the limits and magnitude, introducing the absolute value of a and recognizing the transform form. We conclude that time scaling results in an inverse scaling in frequency along with an amplitude factor. Prove the property of time reversal of the CTFT. We begin with the definition of the continuous-time Fourier transform, which expresses a signal in the frequency domain as an integral over time. We replace the signal with its time-reversed version where time is negated. We introduce a new variable tau equal to -t to simplify the expression inside the integral. We compute the differential showing that dt becomes -d tau due to the change of variable. We substitute the new variable into the integral and update the limits, which are reversed due to the negative sign. We reverse the limits back to the standard order, which removes the negative sign, and simplify the exponential term. We recognize that the resulting integral corresponds to the Fourier transform evaluated at -omega. We conclude that time reversal in the signal produces a reversal in the frequency domain. Prove the property of duality or symmetry of the CTFT. We begin with the definition of the Fourier transform relating a signal in time to its representation in frequency. We also write the inverse Fourier transform, which reconstructs the time signal from its frequency representation. We now interchange the roles of time and frequency variables to explore the symmetry between the two domains. We rewrite the expression by evaluating the time signal at -omega and scaling by 2π. We simplify the exponential expression to match the standard Fourier transform structure. We recognize that the transformed function in time corresponds to a scaled and reversed version in frequency. We conclude that there is a duality between time and frequency where the roles can be interchanged with a scaling and sign change. Prove the property of differentiation in the time domain of the CTFT. We begin with the definition of the continuous-time Fourier transform, which expresses a signal in the frequency domain as an integral over time. We now take the Fourier transform of the derivative of the signal with respect to time. We apply integration by parts by selecting appropriate functions for u and dv to simplify the integral. We substitute into the integration by parts formula, obtaining a boundary term and a remaining integral. We evaluate the boundary term, which goes to 0 under standard assumptions, and simplify the remaining expression. We recognize that the remaining integral is the Fourier transform of the original signal multiplied by j omega. We conclude that differentiation in time corresponds to multiplication by j omega in the frequency domain. Prove the property of differentiation in the frequency domain of the CTFT. We begin with the definition of the continuous-time Fourier transform expressing the signal in the frequency domain. We take the derivative of the Fourier transform with respect to the frequency variable omega. We move the derivative operator inside the integral, which is valid under standard continuity conditions. We compute the derivative of the exponential term with respect to omega, which introduces a factor of -j times t. We rearrange the expression by factoring out the constant -j from the integral. We recognize that the remaining integral corresponds to the Fourier transform of t times the signal. We conclude that multiplication by time in the time domain corresponds to differentiation in the frequency domain. Prove the property of integration in the time domain of the CTFT. We define a new signal as the integral of the original signal from -infinity up to time t. We take the Fourier transform of this new signal by substituting it into the transform definition. We express the result as a double integral over tau and t. We change the order of integration, which allows us to integrate first with respect to t. We evaluate the inner integral of the exponential function with respect to time. We substitute the limits of the inner integral and simplify the resulting expression. We recognize that the expression produces the Fourier transform scaled by 1 over j omega along with an additional delta term at 0 frequency. We conclude that integration in time corresponds to division by j omega in frequency with an added impulse term. Prove the property of J convolution in time domain of the CTFT. We begin by defining the convolution of two signals as an integral over a shifted version of one signal multiplied by the other. We take the Fourier transform of the convolution result using the standard definition. We substitute the convolution expression into the Fourier transform integral, resulting in a double integral. We change the order of integration so that we integrate first with respect to time and then with respect to tau. We introduce a new variable to simplify the shifted argument and rewrite the exponential accordingly. We separate the exponential into two parts, allowing us to isolate terms that depend on different variables. We recognize that each integral corresponds to the Fourier transforms of the individual signals. We conclude that convolution in time corresponds to multiplication in the frequency domain. Prove the property of K convolution in frequency domain of the CTFT. We begin with the inverse Fourier transform representation of the signal in terms of its frequency spectrum. We consider the product of two signals in the time domain. We substitute the inverse Fourier transform expressions for both signals into the product. We expand the expression into a double integral involving both frequency variables. We now take the Fourier transform of the product using the standard definition. We rearrange the order of integration and group the exponential terms together. We evaluate the inner integral, which produces a delta function that enforces a frequency relationship. We use the delta function to simplify the double integral into a single convolution integral. We conclude that multiplication in time corresponds to convolution in frequency scaled by 1 over 2 pi. Prove the property of L. Additional properties, even functions of the CTFT. We begin with the definition of the continuous-time Fourier transform, which expresses the signal in the frequency domain. We assume the signal is even, which means the signal evaluated at t is equal to the signal evaluated at negative t. We split the integral into two parts, one from 0 to infinity and the other from negative infinity to 0. We perform a change of variable in the second integral to express it in terms of positive time. We use the even property to replace the signal evaluated at negative time with the signal at positive time. We combine the two integrals into a single expression involving a sum of exponentials. We conclude that the Fourier transform of an even signal is real and can be expressed using a cosine transform. Prove the property of L. Additional properties, odd functions of the CTFT. We begin with the definition of the continuous-time Fourier transform, which expresses the signal in the frequency domain. We assume the signal is odd, which means the signal evaluated at t is the negative of the signal evaluated at negative t. We split the integral into two parts, one from 0 to infinity and the other from negative infinity to 0. We perform a change of variable in the second integral so that it is expressed in terms of positive time. We apply the odd symmetry property to replace the signal at negative time with the negative of the signal at positive time. We combine the two integrals into a single expression involving a difference of exponentials. We simplify the expression using the definition of the sine function, which introduces an imaginary factor. We conclude that the Fourier transform of an odd signal is imaginary and can be expressed using a sine transform. Prove the property of L. Additional properties, real functions of the CTFT. We begin with the definition of the continuous-time Fourier transform of the signal. We take the complex conjugate of the Fourier transform expression. We apply the conjugate operation inside the integral, which affects both the signal and the exponential term. Since the signal is real, the complex conjugate of the signal is equal to the signal itself. We rewrite the exponential term to express it in terms of negative omega. We recognize that the resulting expression matches the Fourier transform evaluated at negative omega. We conclude that for real signals the Fourier transform satisfies conjugate symmetry, meaning the transform at negative omega is the complex conjugate of the transform at positive omega. Prove the property of M. Parseval's relation of the CTFT. We begin by defining the total energy of the signal as the integral of the squared magnitude over time. We express the signal using its inverse Fourier transform representation in terms of its frequency spectrum. We substitute this expression into the energy formula and introduce the complex conjugate of the spectrum. We rewrite the expression as a double integral separating the frequency and time variables. We rearrange the order of integration so that we can evaluate the inner integral first. We recognize that the inner integral is the Fourier transform of the signal, which gives the frequency representation. We simplify the expression, obtaining the squared magnitude of the spectrum. We conclude that the total energy in time is equal to the total energy in frequency scaled by 1 over 2 pi.
And be not conformed to this world, but be ye transformed by the renewing of your mind, that ye may prove what is that good, and acceptable, and perfect will of God. Romans 12 verse 2.